In our study of solutions, we've looked at concentrations, but I want to show you one other scale to measure a property of solutions, and that's pH and pOH for acids and bases. That's what this lesson's going to cover. I want to start with just some of the properties of acids so you can think of some examples that you probably already know about. Acids generally taste sour. Think about a lemon. They do turn litmus paper red. Litmus is an indicator that just tells whether a substance is an acid or a base. So acids turn litmus red. There's another indicator called phenolphthalein that would stay colorless in the presence of an acid. Now acids are good electrolytes. That means they conduct electric current. They do react with some metals to form hydrogen gas. Think about the reaction in a previous lab where we added the zinc metal to the hydrochloric acid and you saw all those bubbles form. Now on the pH scale, acids range from 0 to 7. And then the way you identify the formula for an acid is that it will generally begin with a hydrogen atom in the front. Let's compare this list to the properties of bases. Bases, instead of being sour, are bitter to taste. Think about soap if it's ever gotten in your mouth. Bases are slippery to touch. They turn litmus paper blue. Remember that acids turned litmus paper red. The phenolphthalein indicator in the presence of a base turns a magenta color. It's a really dark, hot pink color. Bases are also good conductors of electricity. Their pHs are higher on the pH scale. They range from 7 to 14. And finally, the way to identify a base on paper, or if you're looking at its formula, is to look for the hydroxide polyatomic ion, OH, which is going to come at the end of the formula. Now when acids and bases react together, they neutralize one another. You've seen commercials for Tums and Maalox and products like that that neutralize excess acid. Well, what's happening is you're taking a base and reacting it with the acid that's in your system. So acids and bases neutralize one another. And the most generic form of the equation is what I've given you here. An acid and a base will react to form a salt and water. Now a salt is not necessarily sodium chloride that's in your kitchen. A salt is a compound that is made from the cation of a base and the anion of an acid. So there are other formulas for a salt. The way that you monitor these acid-base reactions is to use an indicator that changes color. For example, the litmus or the phenolphthalein that I showed you on the list of properties for acids and bases. Now, when an acid and a base react, sometimes it's useful to do some calculations to go with those reactions. I want to talk to you a little bit now about the hydroxide and the hydronium ion concentration. The hydronium ion, or H+, indicates an acid unit of a substance, and the hydroxide ion, which is OH negative, indicates a base unit. Now for a substance like water, which is neutral, the concentration of hydronium and hydroxide are equal. And studies have shown us that the value in water is 1 × 10 to the -7th molar. Both those concentrations are equal in any neutral substance. Now the hydronium and the hydroxide concentrations are related. So if the concentration of one of them goes up, the concentration of the other one goes down. We find that the product of the two is a constant. That's going to lead us to pH. Now pH comes from a French term that means hydrogen power. If you have a substance that is neutral with a pH of 7, that means that the hydronium ion concentration is 1 × 10 to the -7 molar. Do you see how that exponent in the concentration is the pH value? That's going to be useful in a few minutes. If a substance is acidic and the pH is less than 7, then we have lots of acid units in the substance. So the hydronium ion concentration is going to be greater than 1 × 10 to the -7 molar. And then finally, if a substance is a base and the pH is higher than 7, the acid concentration is very low. So it's going to be smaller than 1 times 10 to the minus 7th molar. The calculation we're going to use for pH is given here. It's equal to the negative log of hydronium ion concentration. Now H3O plus is the exact same as H plus on that top part of the slide. So that formula is in your reference packet. Let's use it to do some calculations here in a minute. There's a couple other formulas you're going to find useful. Just like there's a pH scale, there's also a pOH scale, and that gives us the power of the hydroxide ion, or the base unit. The pOH is equal to the negative log of hydroxide ion concentration. Now this isn't a scale that scientists normally use. Everybody just does pH. But it is out there, and the reason it's helpful is because of this last formula. It turns out the pH plus the pOH will always equal 14. So for example, if we have a solution that has a pH of 2 and it's acidic, I know its pOH must equal 12 because 2 plus 12 equals 14. Alright, so now we're ready for those examples. In this first problem, we are trying to figure out the pH if the hydronium ion concentration is 1 times 10 to the minus 7th. So I'm going to use that new formula to find the pH. I can plug the 1 times 10 to the minus 7th molar in for that concentration of hydronium. When I plug that in, I'm going to enter it in my calculator exactly the way it's written, negative log 1 times 10 to the minus 7th. And when you do that calculation, you get a pH of 7. This is a neutral solution, just like water. Let's look at the second problem. We have to calculate pH, but we're given the hydroxide ion concentration is 1 times 10 to the negative 8th. So I think what I'm going to do is to rely on this formula. pOH equals negative log of hydroxide ion concentration. I'm going to plug in the 1 times 10 to the negative 8th molar there, and when you put that in your calculator, you're going to find that the pOH is equal to 8. If the pOH is 8, I know the pH has to be 6, because those two numbers will always add up to 14. By looking at the pH, and I know it's less than 7, this is an acidic solution. Now here's the last chart. The first row of the table is given to you. They give you the pH is 4, so you know the hydrogen ion concentration, or hydronium, is 1 times 10 to the negative 4 molar. Remember that the pH is the exponent in the concentration. The pOH is 10, because pH and pOH have to add up to 14 every time. So if the pOH is 10, the hydroxide ion concentration is 1 times 10 to the negative 10th. And then because the pH is 4, this is an acidic solution. Now we're going to go through each one of these. The numbers in black are given to you in your table, and the numbers in red have been calculated. So the first one that's here for us to work out is number 2. They give you the pH is 9. If the pH is 9, the hydronium ion concentration is 1 times 10 to the minus 9th molar. So I filled that in for you. Now the other thing I know is that if the pH is 9, the pOH is 5. So I filled that in. And if pOH is 5, hydroxide ion concentration is 10 to the negative 5th molar. Look at the pH every time to decide what type of solution you have. If the pH is 9, this is a base. Now take a look at number 3. I know it's exactly the same as number 2, but they gave me a different number to start with, which was the hydroxide ion concentration. 10 to the negative 5th molar for hydroxide gives me a pOH of 5. If pOH is 5, pH is 9, because 5 plus 9 is equal to 14. If the pH is 9, then the hydronium ion concentration in the first column is 10 to the minus 9th molar. Again, the pH of 9 tells me this is a base. Okay, and the last one, They give me the hydronium ion concentration is 10 to the negative 1 molar. The pH of that, or the negative log of 10 to the negative 1, is 1. So this is a pH of 1, and that is an acidic solution with a pH that low. The last thing I need to figure out is the hydroxide ion concentration and the pOH. Well, pOH has to be 13 because 1 plus 13 is equal to 14. And if the pOH is 13, the hydroxide ion concentration is 1 times 10 to the negative 13 molar. So how is all of this measured? Well, the type of lab that we do is called a titration lab. It's a method where you take a known solution, and when I say known, you know its concentration, and you use that to determine the concentration of an unknown solution. The reaction we're going to do in lab is set up similar to this diagram. You have a big glass burette that has the base sample in it. You pour the base into the acid, which is in the flask below the burette, and you mix them together. A neutralization reaction occurs, and you put an indicator in the acid solution, and when the pH begins to change immediately, your indicator will change color. That tells you that all of the acid has been neutralized. From there, you can do a few calculations to figure out the concentration of your unknown acid. So that's a brief introduction. We'll work some more next time. Have a good one.